Good morning, or good afternoon, depending on where you are. My name is Professor Orata, and we are continuing with our thermodynamic lectures. Today we want to look at gases, special emphasis, real gases. Special emphasis on real gases. Now, you're all familiar with gases. We know that air is a gas and it has several components, different types of components. We have nitrogen, we have oxygen, carbon dioxide, all manner of components. But we assume that relatively this composition is constant. So when you're dealing with air, we don't worry about its components. You just say it's a gas and you assume those components are relatively stable. It's a stable system. Now, when we are dealing with gases, one of the very fundamental characteristic equations that you are familiar with, or equations of state, is the ideal gas equation, which is PV is equals to nRT. This ideal gas equation of state, of that particular characteristic equation, relates pressure, volume, temperature, and the quantity, the amount of gas. So most of the times, we assume that gases behave ideally. And when we assume they behave ideally, then it means that we are assuming that they obey this equation of state. The other equations of state, the Van der Waals equation of state, is a fundamental one. Then we have the Beatty-Bridgman one. We have the Bartolotti equation of state, the Redlich-Kwong equation of state, Varial equation of state, and there are many more equations of state which will come to try to rationalize these properties of gases based on empirical data. Now, let us recognize a few things about gases. One, we know that gases are permanently, the gas molecules are permanently in a state of motion. This is the fundamentals of the kinetic theory of gases. And we have always assumed in the case of ideal gas that the volumes of these molecules are negligible compared to the volume of the total system. And we are also looking at the pressures, the pressure component. That is where, what is pressure? Pressure is when these molecules collide with the walls of the container or the containing system, then pressure is exerted. So in the Van der Waals variant of the ideal gas equation of state, it is factored in, that element is factored in. This element is factored in of pressure and the element of volume. Now, when we are thinking of real gases, we want to move in the direction where we look at the behavior of gases towards the ideal gas equation of state. And one of the fundamental things is the compressibility factor. The compressibility factor. Now, the compressibility factor, Z, is PV over RT. That's the compressibility factor. PV over RT. And so, gases which are behaving as ideal gases are assumed to have a compressibility factor of 1. Remember that most gases behave as ideal gases in the limit of low pressures. As you lower the pressure, the gases approach ideal gas behavior. So in the same way, we are going to see when we are talking about reduced variables that the reduced pressure tends towards 0, then it approaches, the compressibility factor approaches 1. And so it's ideal. Now, for ideal gases, they tend towards 1. Now, if you look at the compressibility chart, take the case of a compressibility chart, and I'm going to use terms which I'm going to qualify later. If you look at the compressibility chart, so we have Z and the reduced pressure. And we are saying that gases behave ideally when this value is 1.00. Now, that is a tall order for most of the systems. We normally assume it in our calculations, but it's a tall order. It's a tall order. So most gases will not exactly tend towards that, but at low pressures, maybe they may tend towards that. So you find this type of profiles. So this particular one, you can say slightly approaching ideality. Let's say this particular curve here, this A, curve B, curve C. We are seeing that this one is approaching more of the ideal behavior. And this is at different reduced temperatures, In this particular case, what I'm talking about, reduced temperature here, let's say is 2.00. Let's say for this one, the reduced temperature here is 1.50 and so forth. Now, what is a reduced variable? What is a reduced variable? So this is our compressibility chart. What are reduced variables? Now, reduced variables are cases where that variable is divided by its critical component. If it is temperature, it's divided by the critical temperature. If it's volume, it's divided by the critical volume. And if it is pressure, it's divided by its critical pressure. So the variable relative to its critical value. What does this mean? If you look at the pressure volume diagram, pressure volume diagram, we will see that at different temperatures, if you decide to compress the gas, that is to reduce the volume, if you compress the gas under constant temperature, we will get this kind of a profile. As we are reducing the volume of the gas, the pressure is increasing. Remember, Boyle's law, pressure is inversely proportional to volume. So as you reduce the volume, the pressure goes up. Now, pressure is increasing. At this particular point, there is no change in pressure. There's no change in pressure. And if we have liquid, for instance, we have liquid, here we have liquid plus vapor, and here we have vapor. So these are the superheat regions and so forth and so forth. Now, we are having this pressure is relatively constant. And then when you reach this particular point, you are trying to compress liquid. So the pressure goes up. This is probably temperature T1. Then at temperature T2, you get the same pattern. Then we have, this is referred to as the critical pressure and critical temperature point. So we have the critical temperature at this particular point, TC, on to critical temperature. Along those lines now, we will have that kind of a curve. And those above are relatively having the same pattern, above the critical temperature. Now, what do we say? We say that above the critical temperature, if you look at these isotherms above the critical temperature, you are seeing that they are almost the same. So we say that in general, it is thought that at twice its critical temperature, most of the gases behave like ideal gases. What does that mean? At twice its critical temperature, twice C, most gases behave as ideal gases. Most gases behave as ideal gases. That's one thing which we need to know. So let us now look at the critical variables which you're talking about. So when we are now talking about critical variables, I want to use that space here. When we are talking about the critical variables, we call them reduced variable when you divide the temperature by the critical temperature. By that temperature divided by that critical temperature, for that particular gas, you get the reduced temperature. This is critical, and this is reduced temperature. In the same way, if you divide the volume with the critical volume, you get the reduced volume. And if you divide pressure with the critical pressure, you get the reduced pressure. So what are we saying? We are saying that for these gases, averagely, when you are twice its critical temperature, they behave like ideal gases. So what does that mean? We have seen that TR is equals to T over TC. So at twice, if the temperature is twice the critical temperature, then they behave like ideal gas. So what's the value of TR? TR will be 2TC over TC over TC. So TR will be 2. So what are we saying? So when we have the temperature, the reduced temperature of this gas, of this particular gas, is about 2.0, we expected it, pay attention, we expected it to behave like an ideal gas. In other words, this curve should collapse, should be closer to this curve of the ideal gas. Let's mark that as ideal gas. Very important for us to note that. Very, very important for us to note that. Now, this is an important aspect of real gases. That's an important aspect of real gases. Now, the other important aspect when we are dealing with these real gases, is normally the assumption that heat capacity is always assumed to be constant. We always assume heat capacity is constant. We always assume Cp and Cv are constant. Cp is the isobaric heat capacity. Cv is the isochoric heat capacity. By now we know that that is basically del U del T, V constant, and this is del H del T, P constant. Now, we always assume that the heat capacity is constant. That is not true. In fact, there is normally functional dependence of heat capacity on temperature. When we derive the Kirchhoff's law, if you go to the thermochemistry lectures, where we derive the Kirchhoff equation, we put a caveat on that assumption and showed how we would use it if that's not the case. So in general, for heat capacity, Cp can take the form A plus Bt plus Ct squared plus, I just truncated it at the third term. Now, and so if that is the case, then it means that if that is the case, what does it mean? It means that when we are dealing with issues of heat capacity, we must take cognizance of this fact here. Because remember, dH over dt is equals to Cp. So if we arrange and take limits, integrate over certain limits, let's call I to F, then we will have Cp dt. We used to assume this is constant, so we write that out as IF dt. And now you are saying this is assuming is constant. So you can kick it out of the integral bracket. But now we are saying that there is a functional dependence on temperature. So you need to take cognizance of that particular fact. So that means that the integral of dH from some limit should now be A plus Bt plus Ct squared. As I've said, I've truncated it, dt. So that what you now get is you'll have AT plus BT squared over 2 plus CT cubed over 3 Fi. Remember when we have written A, Fi is simply the value of A at F minus the value of A at I. So don't get confused. So you can do that opening up of that particular expression there. And so in general, remember in general, we say that the profile for the heat capacity with temperature in general, profile for heat capacity, take the isobaric one, temperature, then you're going to get something like that, profile for heat capacity. Don't confuse when you talked of phases, you talked of helium, phase diagram, pressure versus temperature, and you talked of lambda line, which was called lambda because of the behavior of the heat capacity curve. Now, so that is CP and T. The other thing which you need to worry about when you're dealing with real gases, so that some of those assumptions which you have always assumed are taken care of in reality, is the simple facts to do with entropy. And to develop the concept of entropy, we are going to approach it from a two-pronged approach. One, using fundamental thermodynamic state function expression, H is equals to U plus PV, and the Clausius inequality. The Clausius inequality, which you are now familiar with, which says that ds is greater or equal to dq over t. Now, let's work with this. Two quantities. So, the framework of our discussion to develop the entropy expression for our real gas at some given limits, probably some pressure and some temperature, is going to be based on these two fundamental thermodynamic expressions. Now, let us get the change in H. So if you take the change in H, we consider du. dH is equals to du plus pdv plus vdp. But remember from first law of thermodynamics, from first law of thermodynamics, du is equals to dq plus dw. And if we plug in place of dq the Clausius inequality expression, then dq will be TdS. That will be TdS. And for PV work, remember, we said that dW, for PV work, dW is minus PdV. This is for PV work. Always remember that. And I said there are other forms of work. You can have electrical work, which you can calculate, multiply current, potential, and time, and so forth and so forth. And you can work with that. Now, so if we use that expression, so this is minus PdV. So we can use this expression here. We can take it back there. So what do we have now? What do we have? We now have dH will be equal to TdS minus PdV plus PdV plus VdP. So those two will cancel. So we have dH is equals to TdS plus VdP. dH is equals to TdS plus VdP. But what is dH? We already know dH. We already know, just take note. We know that dH over dt is equals to Cp, which implies that dH is equals to Cp dt. So we are going to use that expression here. We are going to use that expression there. We have TdS. Now, if we assume the gas behaves ideally, if we assume ideality, ideal behavior, and I want you to take note of this. You see, when we are talking of using this characteristic equation, PV is equals to nRT. Now, we have talked of Van der Waals equation. So P plus A over V, V minus B is equals to R, is equals to RT. That's the van der Waals equation. Van der Waals equation. Now, you should not panic. You should not panic because we're talking of this characteristic equation, ideal gas equation of state. If I want to work with ideal gas equation of state, just the same way I would integrate P dV in the system, for example, for DW, let me give you just an example. I want to give a quick example. We have said du is equals to dw for adiabatic processes, because dq is equals 0 for adiabatic process. Adiabatic process. Now, this du from Joule's experiment, if you go back to our discussions, you will find that this is Cv dt is equals to minus P dV. And so you proceed with simplifying that. That is minus nRT over V is equals to Cv dt. Then you can proceed with calculus to sort things out. Now, I want you to get this point. Suppose you are now using another equation of state, van der Waals equation of state. What you do is very simple. In place of P here, make P the subject here. So if you come to the van der Waals equation there, then we are saying that P plus A over V, divide throughout by that, that will become RT over V minus P. That becomes RT minus P. Therefore, P is equals to RT over V minus P plus A over V. Then I will take this quantity here and plug it in place of P there and proceed. So I'm using that characteristic equation now to solve my problem. You can use more complex one. Already Kwong equation has very many constants and variables. Very many constants. So you might use iterative processes to solve it. Very intense numerical analysis methods. Now, so I'm just saying you can use any equation of state. Just be patient. Just work out what expression for pressure is, and then now when you are dealing with this in terms of integration, you'll be integrating a very bulky quantity there, so you will have to use a little bit of more identities in integral differential calculus. Now, we said that this quantity we can take it back there. Now let's work our way now. We want to see the expression for entropy for this real gas. So what do we have now? So we am here now putting back. I've already put that there. So we have CPDT is equals to TDS plus V. We have said we are assuming that this is ideal. So V in that case will be nRT over P. Let's assume we are dealing with unit amount. So let's just have RT over P. So if I plug this one here also, I put it there. I put it there. This particular one, I put it in place there. So I have dx is equals to RT over P, dP over P. RT, dP over P. I have put it in place of V. So I put RT over P, which is, I've just rearranged my system there. So if I divide throughout by T, I can divide throughout by T, dividing throughout by T. I will have Cp dt over T plus is equals to ds plus R dP over P. So I can choose to integrate over some limit. I can have my base value. Let's say I assume that the initial state, we assume corresponds to the coordinates P naught, T naught. And some final state will correspond to some coordinate. And the final state, some coordinate px, tx. It can even be phases, alpha phase, beta, and so forth. So it doesn't matter. That's just an assumption I've made that that would be my initial state, my reference state. Now, if that's my reference state, so now if I integrate on integration, if I integrate this quantity, differential calculus, very important. Always remember the identity. If you integrate xn, you get xn plus 1 dx. And if you integrate dx over x, you get natural log of x plus c. These are very important identities in integral calculus. Now, so if I integrate those quantities, I have Cp dt over t from some value t naught to tx is equals to integral dx from some value, yes, plus r integral from P naught, okay, that's now the pressure limits, to dP over P. And so I will use this identity. You have that identity there, the second identity which you put there. So in that particular case, we are if I assume that I don't want to go to the business of using Cp as a function of temperature, then I will simply have Cp in Tx over T naught. In fact, let me not go into that. Let me just leave it so that you can battle with it. Put A plus BT plus CT squared there and solve it. So I will not solve it. I will just leave it at that, and I will not assume it is constant because we're dealing with real gases. So I just solve for delta ds. So the integral of ds, remember we said dx, the integral of that is simply x. So what we have here is will be s into t naught tx minus s into t naught is equal to the integral t naught tx cp dt over t. Remember that's natural log of t, tx, natural log of tx over tx minus natural log of t naught over t naught, and you go solving the problem. And then I take this one, that side. Where did we leave our r? I think there was r somewhere. There r somewhere. We have just forgotten it. It has just, we have left it. It was r here. There's r there. So that our r is there. We have forgotten to write it down. So plus r, of course, is a constant, gas constant, from P naught to Px dP over P. This expression you use to compute the entropy of a real gas. Real gas. That's the expression which you will use to compute the entropy of a real gas. I repeat. One, real gases, we use reduced variables. Now, that concept of reduced variable is fundamental. For example, we have said we have reduced volume, VR, which is the volume of a VC, critical volume, reduced pressure, PR, which is the pressure of a critical pressure, reduced temperature, which is temperature over critical temperature. Now, these three variables, if we have two gases which have the same value of reduced volume, for example, and reduced pressure, then there is a likelihood that those two gases will have the same reduced temperature. I repeat, if there are two gases and, for example, they have the same reduced pressure and reduced volume, then there's a likelihood they'll have the same reduced temperature. Or if they have the same reduced temperature and the same reduced pressure, there's a likelihood they'll have the same reduced variable. And that's the law of corresponding states. So let's just summarize what you have said. One, real gases, not necessarily obeying the characteristic equation PV is equals to nRT. There are many other equations of state. Even you can develop an equation of state based on empirical data. I believe as time moves on, there are all going to be all manner of variations in terms of the characteristic equation, given the sophistication in numerical technology. Now, two, we are saying that if you look at the compressibility chart, despite the fact that we say that isotherms above the critical temperature in the pressure volume system, which we had shown you there, that even if we think that when the temperature is twice its critical temperature, it behaves like an ideal gas, there's definitely deviation on the compressibility chart. When TR is equals to 2, you don't see it overlap completely that. And number 3, heat capacity. We have always assumed Cp and Cv are constant, but that's not necessarily the case. So you need to use the refined one where temperature is taken into account, and you're able to compute the entropy. Entropy using the thermodynamic variables which we built this framework for this equation on.